let's look at section 9.8 and talk about power series. So let's begin with a definition. Okay. Let's begin with a variable. We'll call it x, as usual. Then the sum, as n goes from 0 to infinity, of a sub n x to the power n, which is equal to, well, let's see, if n is equal to 0, that's a sub 0 x to the 0 power. Okay, well, that would just be 1, plus a sub 1 x to the first power, plus a sub 2 x to the second power, plus a sub 3 x to the third power, plus on and on and on forever. This is called a power series. Here I suppose I should say let x be a variable and a sub n be a constant. So here this a sub 1, a sub 2, a sub 3, these are all constants. Basically, it's an infinitely long polynomial. Normally a polynomial is a polynomial of degree 1, or a polynomial of degree 2, or degree 3. But here you have a polynomial that has no biggest power. It's a polynomial with infinite number of terms. Now, because it has an infinite number of terms, some of the things that we're familiar with about polynomials are just no longer possible. But because it does take the form of a polynomial, and in particular its partial sums are all polynomials, then there are going to be some nice properties that do carry over. Here we're going to go ahead and take a slight variation thereof. The sum, and it's still part of the same definition, the sum as n goes from 0 to infinity of a sub n times x minus a constant to the power n, which is going to be a sub 0, plus a sub 1 x minus c, plus a sub 2 x minus c squared, plus a sub 3 x minus c to the third, plus dot dot dot, is going to be the power series centered at c. All right, where c is constant. All right, so there's our definition. All right, but who cares? I mean, this is an infinitely long polynomial, which means it's going to grow to infinity, right? I have an infinite number of terms that I've added together. Well, as we've seen in the last several sections of this chapter, it depends. Depending on what numbers these happen to be, maybe this will be infinite, in which case, who cares? It diverges. We learn nothing. But if these are small enough, even with an infinite number of them, it may converge to a particular value. Right? So here we're going to say, okay, let's consider, and okay, so that's the end of our definition up there. So now we're going to look at something else here. Let's go ahead and consider this as a function. So f of x is equal to the sum as n goes from 0 to infinity of a sub n x to the power n. You can think of this as a function of x, right? Because after all, these are constants. These are all constants, and so are the powers. They're all constant powers. The variable x is a variable. So you can think of this function being defined as a power series, kind of like saying it's a polynomial function with an infinite number of terms. Okay, well now, if that's a function, I should be able to talk about things that I usually talk about functions. In particular, I should be able to talk about its domain and range. So here, consider the domain of this function. All right, well, if it's a polynomial, it should have an infinite domain. I should be able to plug in anything. Well, yeah, but that's usually what we talk about when we have finite polynomials. Is that still the same for infinitely long polynomials? Well, no, because even if you have a number that can be plugged into, for example, the first 3 terms or the first 4 terms, if you plug it in and you have enough terms, that may grow large enough to have your series diverge. So when we consider the domain, it's no longer enough to say, oh, well, it's polynomial, so then it must have every number in its domain. In fact, what it's going to turn out is you're going to end up with 3 possibilities. So here, I'm going to go ahead and write this. Instead of using this power series, I'm going to say the power series centered at C, because it's just a little bit easier to see what's about to happen. Just a little bit. All right, so let's say I have that power series. And of course, either power series is the same. It's just here, this one's centered at 0, x minus 0 versus x minus some other number. It turns out that for the domain, there's going to be 3 possibilities. Obviously, for any finite number of these terms, any number is in the domain. The problem is going to come from when I have an infinite number of terms. Well, we've seen in previous sections that the problem comes from the fact that the series might diverge. It might go off to infinity. So here's what might happen. You might have that this just diverges. Well, no. It's always going to converge at least for one number. If you plug in C right here, C minus C is equal to 0. So here that would be a number plus a number times 0 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 forever. Oh, so that would just give you that first number plus 0 forever. Oh, but it doesn't matter how many zeros I have. I can have an infinite number of zeros. 0 plus 0 plus 0 plus 0 forever is still 0. So here, at the bare minimum, I should have that this series will converge when x equals to c. Okay, so my series must converge. And in fact, it'll converge to that first number because all the rest will go away. But here, it must converge for x equal to c. Minimum, no matter what. Because here, if x is equal to c, all of these terms are 0, and you're just left with a single finite value. And that's what we mean by converge. Your series gives you a single finite value. Okay, now, it's also possible that no matter what C I plug in right here, it's possible that no matter what C I plug in, the whole thing will converge. It may be that these numbers are just so small that it doesn't matter how big these numbers are. It doesn't matter how big these get. These are so small that as a sum, I end up with a sum of very tiny terms, which eventually does converge. So it's possible that the series converges for all x. Okay, so imagine your number line. You have a number line. You know for a fact that your series must converge at c. No matter what, doesn't matter what series you have, even the biggest, most ugly looking series must converge at c, at its center. Now it's possible that your series converges for the entire number line. Okay, well, what about in between? Is it possible that I converge more than just at c, but not out to infinity? That's our third possibility. It is possible to have a series that converges over a finite interval. Now, of course, that interval must be around c because c must be included. So here we have the third possibility. It's possible that series converges for only the x in a finite interval, in a finite length interval around c. Okay, so here, this finite length interval could go out as far in one direction as it can in the other direction. It'll be symmetric. And from here, the maximum value you can achieve is c plus some amount. Now here, I'd almost be tempted to use epsilon, but no one ever said that had to be a small amount. That could be pretty big. All right? It can be big as long as it's still finite. And over here, this would be c minus r. This value r, which tells you how far away from your center you can go, is called the radius of convergence of your series. So if you're going to define a function using a power series, the first thing we want to do is we want to figure out where does it converge. If it only converges at one point, well, okay, fine, but I guess that's fairly useless everywhere except at that one point. So maybe we don't want to worry about it like that. Maybe we don't want to do it like that. Now, if it converges for every value, well, then that's great, because that means I don't have to be careful. This will always converge, so I can plug in whatever I want. The third possibility is the one that's a little bit, you have to be a little bit careful about that one. And that's, yes, it will converge, but only sometimes, only for some values of x. And you have to be careful because your domain is restricted. It's only between here and here. Okay? So this gives us a theorem which essentially formally states what I've drawn crudely up here. Theorem. We're going to begin with a power series centered at C. So let f of x be defined as a power series n from 0 to infinity of a sub n at x minus c power n be a function defined by a power series. Centered at C. Okay? If that's the case, exactly one of these is true. Exactly one of the following is true. Either your function is convergent only at C, meaning the domain of the function is exactly C. It's possible that the series converges only at the interval, or let's put it this way, only for x such that the absolute value of x minus c is less than some value of r. In other words, the domain of f is, I guess that would be from minus r to, yeah, so that would be c minus r to c plus r. And 3, the series converges for all real numbers. Converges for all x. So the domain of f is the entire number line. Okay, great. So we don't have a lot of options, which is nice because there's not too many different things that can happen. Okay, but how do I figure out which is the right one? How do I know if my series is basically useless everywhere except at a point? If it's going to converge for everything no matter what, or if I have to be careful and restrict myself to some finite interval? Well, we already know how to do that. We already know how to test if a series converges or not. So consider the following. The question is to find the radius of convergence. The radius of convergence is, again, this number here. How far out from your center can you go in either direction? If you're in the first case, if the series converges only at C, that means that your radius of convergence will be 0. Because you're at C and can't go away from there. Radius of convergence is 0. On the other hand, if you can go out as far as R away from your center, well, then the radius of convergence must be R. And if your series converges for all real numbers, well, that means you can go forever in any direction away from C. So here the radius of convergence is infinite. All right, this is a slight abuse of notation. Usually we wouldn't say the radius of something is infinite because, of course, a radius is supposed to be a finite number. But here, all that's meant is, oh, you can go forever in either direction. It's an abuse of language and abuse of notation, but as long as we're careful with what that means, it is a nice short way of saying that. So let's find the radius of convergence of the series. Sum as n goes from... Oops, I grabbed the wrong color there, didn't I? Here we go. The sum as n goes from 0 to infinity of 2x to the power n. All right. We know how to find whether or not a series converges. And you say, well, yeah, but that was only when I had constants here, right? I never had a variable before. This is still a series, though. And we should still be able to test whether or not it converges using one of our convergence tests. Here, I'm going to go ahead and use the ratio test. Whenever you're looking for series for the radius of convergence, a ratio test will often yield you some good results, mostly because of what it is that we're trying to do. We're trying to find the value of x. You could use the root test as well. The root test often gives you some good results. For finding the radius of convergence, root and ratio tests will often yield you all you need. If those are inconclusive for some reason, then we try one of the other ones. Right? So for a power series, with a series that has variables to a power, root and ratio tests are usually the way to go. So here, let's say, I'm going to go ahead and test the convergence and I'll go ahead and use the ratio test. And that's just because I have to pick one. I could have picked the root test as well. Okay, well, the way the ratio test works is I need to take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, and see what happens to those. Okay, well, that's going to equal to the limit as n approaches infinity of, here I'm going to have n plus 1, over, here I'm just going to have power n, like that. Okay. Well, now that's going to give me, let's see, limit as n approaches infinity. Here I can just write that as 2x times 2x to the power n. All right, after all, that's 2x to the power 1. That's 2x to the power n. And if I multiply those together, I get 2x to the power n plus 1 over 2x to the power n. All that's in absolute values. And now I notice that this divides away. Okay, so now here I get that this is equal to the limit as n approaches infinity of 2x in absolute values. Well, that seems a little strange. I was supposed to get a constant, right? I was supposed to get, in the end, a constant. But here, if I take n approaches infinity, I just get 2x in absolute values. Right? There is no n here, so there's nothing to change. Okay, so what? Well, remember, the ratio test tells me that this will converge as long as this number is less than 1. You say, well, yeah, but that's not a number. Well, sure it is. A variable is just a number we don't know yet, yeah? It reminds me of my sister's a kindergarten teacher. A stranger is just a friend we haven't met yet, right? A variable is just a number we haven't met yet. So here, we know that this series will converge if 2x in absolute value is less than 1. Oh, but that's what our radius of convergence says. Our radius of convergence says as long as you stay within a certain range of your center, you're guaranteed to converge. That must be my radius of convergence. But you say, well, wait a minute. I thought over here was supposed to be x minus c. You don't have a minus anything here. Oh, well, sure I do. You just say minus 0. Oh, yeah, that makes sense, because here this is centered at 0. I don't have an x minus anything. Or I could think of this as x minus 0. But then you say, well, what about that 2? Isn't that in the way? Well, yeah, that is in the way. Because we're just supposed to have x minus a constant. Now, that constant can be 0. We can have a series centered at 0. So here we should have either x, or if you want to think of it as x minus 0, that's fine. But here that 2 is in the way. Okay, so then that means, well, 2 is a positive number. Yeah, so, well, that means it doesn't need to be inside the absolute values. I can just write this as 2 times the absolute value of x is less than 1. And now if I move that over to the other side, that's going to give me absolute value of x is less than a half. Ah, there we go. Now that looks just like this, which means that that r, that 1/2, that's my radius of convergence. So here the radius of convergence of this is 1/2. Okay. Note that your center is equal to 0. So by putting those together, you can actually form what's called the interval of convergence. You know your center. That's 0. It doesn't have to be 0, but here it is, because here you're saying x minus nothing. If this was 2 times x minus 5, well then your center would be 5. But here it's 0. And now we're saying that from that center, you can go out as far as 1/2 of a unit in either direction. So here that's minus a half, and that's plus a half. Like that, right? So that means that our interval of convergence is given by the numbers between minus a half and a half. Okay? So here I'm going to go ahead and amend the question, find the radius of convergence and the interval of convergence. Just like that. Okay. Now you say, well, wait a minute. You're supposed to put your parentheses around it, right? You got to be careful now. Remember that the ratio test guarantees you that your series will converge whenever this result is less than 1. It guarantees you that your series will diverge if this result, if this is greater than 1. But finally, remember that your ratio test will fail if this is equal to 1. Yeah, so, well, we know that as long as you're within this region, you're fine. We know that as long as you're outside this region, your series must diverge. No question. That's what the ratio test tells us. What we don't know is what happens when we're exactly at the boundary points. So whenever you're looking for an interval of convergence, you have to test the boundaries separately. Since 2 absolute value of x equals to 1 is inconclusive when using the ratio test, and the same thing will be true for the root test, we have to test these cases separately. So how do we test them separately? Well, we just take those numbers and plug them in, and we see what happens. So here, let's go ahead and do that. Let's go ahead and test the endpoints of the interval. All right, let's go ahead and start by testing x is equal to 1/2. All right, well, if x is equal to a half, my series, well, I don't have a mysterious variable. Now it's just the number 1/2. So let's plug that in. So that's going to be the sum as n goes from 0 to infinity of 2x to the power n. Well, that's going to become, that x is now 1/2. So that is now the sum as n goes from 0 to infinity of, well, half of 2 is 1 to the power n. Oh, but notice that anything, that 1 to the power anything is still going to stay 1. So it's going to be the sum as n goes from 0 to infinity of 1 to the power of just, let's just say 1. Oh, and that must diverge. By the nth term test, here, since the limit as n approaches infinity of a sub n's, well, these are all my a sub n's, they're always the number 1. That's equal to the limit as n approaches infinity of just the number 1. That's going to equal to 1, which is definitely not 0. And the nth term test tells us if you take the limit as n approaches infinity of the nth term, you better get 0, because if you don't, you know it diverges. So this series diverges by the nth term test. All right. Depending on the series, sometimes the two endpoints will diverge, which means you don't include either one. Sometimes they both converge, which means you're going to have to include both of them with a square bracket. And sometimes it'll just be one but not the other. So here we find that if x is equal to 1/2, your series diverges. Oh, that means it can't be in the interval of convergence. So here we're going to use an open parenthesis. All right, now let's do the other one. X is equal to -1/2. Well, that's going to be the sum as n goes from 0 to infinity of 2 times -1/2 to the power n, which is the sum as n goes from 0 to infinity of -1 to the power n. And that is an alternating series. Oh, but the alternating series, the terms don't go to 0. So for the same reason as before, we're going to have divergence. Since the limit as n approaches infinity of -1 to the power n, that one, notice this alternates back and forth between 1 and -1. Every time there's an even power, this is a positive one. If there's an odd power, that's a negative one. So here this will alternate back and forth between even and odd powers, meaning it'll alternate back and forth between positive and -1. Here the series would be something like, well, not something like, it would be, let's see, if you have -1 plus 1 -1 plus 1 -1 plus 1, so forth and so on. And so that would alternate and therefore never converge to anything, which means it would definitely never converge to 0. So again, for the same reason, for the because the nth term doesn't go to 0, this series diverges by the nth term test. Just like that. So over here, we found our radius of convergence was 1/2, and we found that our interval of convergence, well, from your sensor, you're going to go 1/2 in either direction. Here, it was possible that maybe our series converged at the endpoints, maybe one, maybe both, but in this case, it doesn't converge for either. So this gives us our result. We have a radius of convergence is 1/2, which we found from over here. And then our interval of convergence from your center outwards, 1/2 unit. And there we go. Let's go ahead and take another example. Let's consider the series. So example, let's go ahead and find the radius and interval of convergence of the series sum as n goes from 0 to infinity of x, let's see here. Let's go with 3x to the power n over 2n factorial. So go ahead and give this a try. It's going to work the same way that the previous one did. The answer will probably be different, but you're going to start off by testing your series using whatever test is convenient. Here, because of the factorial, you don't have a choice. It's got to be the ratio test. So here, you're going to use the ratio test to find a result. And now using that result, you're going to find your interval, your radius of convergence. Once you have your radius of convergence, starting from your center, your interval goes out either direction from your center. Here, since you're not subtracting anything from x or adding anything from x, the center's got to be 0. So give that a try, pause the video, and whenever you're done, go ahead and unpause the video and we'll go through it together. All right, so let's go ahead and use the ratio test. Here we want to take the ratio of the a sub n plus 1 term over the a sub n term, stick it in absolute values, and take the limit as n approaches infinity. Okay, so that's going to be the limit as n approaches infinity of the absolute value of the n plus first term. Well, that'll be 3x to the power n plus 1 over 2 times n plus 1 whole thing factorial times, and you say, well, no, it's divided by. Well, yeah, but we're going to be dividing by a fraction. So let's multiply by the reciprocal. Here, I'm going to take the a sub n term, which is just that one, and instead of dividing by it, I'll multiply by its reciprocal. So that'll be 2n factorial over 3x to the power n. Okay, now let's simplify that. That's going to equal to the limit as n approaches infinity of, here I notice that I can take 3x to the power n plus 1 and write it as 3x times 3x to the power n. All right, after all, 3x to the power 1 times 3x to the power n is 3x to the power n plus 1 over, here, 2n plus 1 here, that will distribute, so that will be 2n plus 2 factorial times 2n factorial over 3x to the power n, like that. We're not done simplifying yet, but I first of all notice those are gone. So now I end up with the limit as n approaches infinity of, well, that's just absolute value of 3x to the power 1. Or I can just write 3x times 2n factorial. And now this denominator, well, that's going to be 2n plus 2 factorial. Remember how factorials work. That's going to be 2n plus 2. Now count down 1. So that's going to be 2n plus 1. Now count down another one. That's going to be 2n. Now count down another one. That's going to be 2n minus 1. Count down another one, dot, 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 all the way down to 3, and eventually 2, and eventually 1. That's how factorials work. You start from that number and start counting down one at a time until you reach 1 and multiply them all together. But notice that from here on, that's just n factorial. 2n factorial. Starting from 2n, counting down to 1. So here, this 2n factorial makes that 2n factorial go away. They divide out. And so we're left with the limit as n approaches infinity of 3x in the numerator over, I can write that out as 4n plus, that should be 4n squared, plus 6n plus 2. Like that in absolute values. But now notice, x is a constant. You say, no, it's not, it's a variable. Well, for the purposes of this limit, it's a constant. We're taking the limit as n approaches infinity, which means this 3, this 4, this 6, and this 2 are not affected. But neither is this x. N is what's going to infinity. So as far as this is concerned, this is not moving. This is just staying as it is. You can pick different values of x if you like, but it doesn't matter what they are. Once you pick what x is, it's staying fixed. These are growing to infinity. So here you have something that's fixed divided by something that's growing to infinity. Oh, that's going to go to 0. Notice it doesn't matter what x is. So here this is going to equal to 0 for all x. If you had x was equal to 1,000,000, that's 3 million over something that's infinite. Oh, that's still going to 0. If x was 1,000,000,000,000, 3 trillion over something that's going to infinity, that's still 0. Doesn't matter what that is. This will eventually become infinitely bigger. So the whole thing will become infinitely small. It'll go to 0. Oh, but now we know that as long as this number right here is less than 1, then we know the ratio test shows us convergence. Since the limit as n approaches infinity of the absolute value of an plus 1 over an is less than 1 for all x, then that means that the power series, here, let me just write, then the series converges for all x. All right. Over here, it wasn't always less than 1. It was only less than 1 when x was less than a half. But over here, there was no x left. You got this limit was equal to 0 no matter what. Oh, okay, well then that means that this will converge no matter what. So that means that up here, our series has a radius of convergence that's infinite. Infinite radius of convergence. Which means that your interval of convergence is the entire number line. From minus infinity to infinity. Normally we would have to test the endpoints, but here this doesn't have any endpoints. The entire number line goes on forever in both directions. So here, note, for this case, we don't test the endpoints. There are no endpoints to test. So that's it. That's our result. Now, once we have a power series, once you know that it converges, you can do some interesting things with it. Because as long as it converges, then it is a finite value. And as long as it's a finite value, then we can think of it as a polynomial function. Now, it may have an infinite number of terms, but it converges, which means that even if it has an infinite number of polynomial terms, it's still going to give you a finite result. What that means is we can treat them like polynomial functions usually are treated. We have an infinitely long tail of terms, but each of those terms can be treated the way we usually treat the terms of a polynomial. And since this is a calculus class, what we want to do is we want to treat them by looking at the power rule. We want to look at differentiation and integration. So consider the following series. We're not going to worry about where this series came from right now. Just it's a series. So consider f of x equal to x to the n. Oh, that should be a series. The sum as n goes from 1 to infinity of x to the n over n. Okay? Now, remember, this is a sum, an infinite sum, of polynomial terms. That's basically what a power series is. If n is equal to 1, well, that's going to be x to the power 1 over 1. Then, if n is 2, I get x to the power 2 over 2. And then x to the power 3 over 3. And then x to the power 4 over 4, and so forth and so on. Okay? All right, now, here, this series, you can go through and you can check it. All right? You can find its interval and radius of convergence. And I'm going to just tell you what it is here. You can test it yourself to confirm this, but the interval of convergence is from minus 1 to 1. And it doesn't include either endpoint. So here our radius of convergence. Well, let's see. Our center is 0. We're going from 0 one step in either direction, so our radius of convergence must be 1. Okay, so what? Well, this is a polynomial. And as long as your x values are between minus 1 and 1, this thing will converge. Or in other words, this thing is a legitimate statement. It says something. It doesn't just say, oh, here's a bunch of infinite terms that go off to infinity and who cares? We learn nothing about them. So as long as we're in the interval of convergence, we can treat this the way we would normally treat a polynomial. Which means I can take a derivative. If this is a function, and it is, right, it's an infinitely long polynomial function, here the derivative of this is done by taking the derivatives of individual terms. After all, I can take the derivative of x. And you say I have an infinite number of them. So what? I can take them one term at a time. The derivative of x is 1 plus the derivative of x squared over 2. Well, that's going to be x. And the derivative of x to the 3 over 3. Well, I take the 3, bring it down, subtract 1 from the power. That's going to be x squared, and then x to the 3rd, and so forth and so on. Oh, but I can write that in a particular way. I can write that as the sum as n goes from 0 to infinity of x to the n. right? After all, this is x to the 0, x to the 1, x to the 2, x to the 3, and so forth and so on. I could write this as the sum as n goes from 0 to infinity of x to the power n. Because after all, that's what that is. X to the power 0, x to the power 1, x to the power 2, x to the power 3, and so forth and so on. But at this point you say, well, wait a minute. What if it wasn't quite that nice? What if it wasn't just take your number, bring it down, subtract 1 from the power? It has to be. Power series always look like this. The constants may be different. This may not always be 1, 2, 3, 4, 5. Depending on what your series look like, it might be something much more complicated. But individual terms are all monomial, which means it'll always look like that. You say, okay, so then all I have to do is write out the terms and then take derivatives one at a time? Absolutely. But you could do it even simpler because you already have the nth term. So consider this. F prime of x, well here, let me write it this way. F of x is equal to the sum as n goes from 1 to infinity of x to the power n over n. Okay, so now let me take a derivative. Well, if I take the derivative of one side, I have to take the derivative of the other side. This is why convergence is important. If this doesn't converge, then that means that this equal sign is nonsense, right? This function is equal to something that's infinite. Oh, that's nonsensical. That's why we have to stay in the interval of convergence. If we're not in the interval of convergence, this equal sign isn't really a thing, right? F of x can't equal to something that's infinite. It's got to equal to a finite value. So here, in order for this to work, I need these two to be equal. Oh, but if they're equal, I can take the derivative of one side, take the derivative of the other side. And now, you say, well, how do I take the derivative of that? The same way you always take the derivative of monomial terms. Take the n, bring it down, subtract 1 from the power. Right? Take the n, bring it down, subtract 1 from that power, and look, those n's cancel out. Just like that. Oh, okay, so then that's the sum as n goes from 1 to infinity of x to the power n minus 1. Oh, but here, if I start at 1, that's x to the power 1 minus 1, that's 0. And then 2 minus 1 is 1. 3 minus 1 is 2. Oh, you know what? I could just scoot everything over by 1. So here, instead of starting at 1 and saying 1 minus 1 is 0, why don't I just start at 0? So n goes from 0 to infinity of x to the power n, which is exactly what we got over here. So as long as you're in the interval of convergence of your power series, you can treat individual terms the way you usually treat individual terms of polynomials. Because of course this is this actually is equal. These two are, f of x is this convergent series. But now if I can treat these as individual terms, then I can just take the integral of each term and say, oh, well, once I'm done taking the integral of each one, I'm going to add them all together. Integration works the same way. If I say f of x is equal to the power series, sum as n goes from 1 to infinity of x to the power n over n, let's say I wanted to integrate with respect to x. Integrate with respect to x. Notice I said integrate with respect to x. You say as opposed to what? I mean, here technically n is a variable, right? In Cal 3, your next semester, you'll start to see things like that where you have multiple variables and you have to consider them and actually think about which one am I worried about. But here, this looks the same way it usually does, integral with respect to x. All right, now, that's just going to equal to, okay, well, that's the integral of a sum. But integrals are linear operations, which means if I take the integral of a sum, that's the same as the sum of the integrals. So this is the sum as n goes from 1 to infinity of the integral of these terms. Okay. Incidentally, I am glossing over something. Switching these is not automatic. Integral of a sum is not the same as the sum of an integral. And you say, yeah, it is. That's what linearity is. That's what we've been saying since Cal 1, right? Yeah, but we've never set it for an infinite number of terms. You say, okay, so can that be switched? Did you just make a mistake there? I'm glossing over some pretty big stuff right here. Integrals are limits. Summations are limits, right? That's the limit as the number of terms goes to infinity. That's the limit as the norm of our partition approaches 0. Switching limits is actually kind of a complicated thing. But that's another reason why we tell you stay inside the interval of convergence. As long as you're in here, that's valid. And you're not going to have to worry about why it's valid. That's something left for higher classes. If you take analysis, you'll look at that. And that's actually not a trivial thing to switch those. But as long as you're in here, then yeah, it'll work. So this is something we kind of gloss over a little. But let's just say, okay, it works for reasons that are just not ones we can talk about in this class. All right, so here we have the sum of integrals. Oh yeah, but these integrals are easy to take. It's just a power rule. So here that's going to be the sum as n goes from 1 to infinity of, okay, well, take the power of x and add 1 to its power. So instead of n, you have n plus 1. And now divide by the new power. Oh, but you already had an n down here. Okay, that's fine. Let's leave that n down there. Right. Plus some constant of integration. And that's it. This is the integral. Whatever function this was, whatever we defined it as, here we know that it converges as long as you're between -1 and 1. So as long as your x values are between -1 and 1, that's a perfectly valid way of integrating and differentiating. Now, notice that we don't know exactly what that converges to. We said, hey, this converges. What does converge to? Well, we don't know. Oh, okay, well, we found its integral or its derivative. Well, what do those converge to? Well, we don't know that either. We know it can be done. We know that this is the answer, but we can't necessarily express these in a simpler way. So we can't just say, oh, and by the way, this is the natural log of x. Or, oh, and by the way, this is x to the power 7 minus the cosine of x, or anything like that. We won't expect, usually, to be able to say, hey, and by the way, this is equal to something else. These are answers in and of their own right. This is a result. Same thing here. This is a result. In the coming sections, we're going to see something like this expanded to a much more useful conclusion. For right now, it suffices to know, okay, if you have a function that's defined as a power series, as long as you are in the interval of convergence, you can take integrals term by term, and you can take derivatives term by term, just the way you normally would for a polynomial function. Right? If you're not in the interval of convergence, this may not be true, and in fact, generally it's not. In later sections, we'll take that to a more robust conclusion, to a conclusion that's a little more meaningful than just, oh, and by the way, here's a computation. All right? But for now, as long as you know how to find radii and interval of convergence, and as long as you keep this in mind for later use, that's all we worry about for this section. And that brings us to the end of the section. So for an assignment, you might want to practice some of this stuff. Try section 9.8, do problems 5 through, 5 through, let's say 35 odd. We don't need to do those last two. And then let's try problems number 49 and 51. Those are just problems like this where you're going to take a series, and then once you confirm its interval of convergence, it's going to ask you to take a derivative and an antiderivative. And again, it's just, as long as you stay in here, you just do it term by term. If anybody has any questions, please make sure you make a note of them and get in contact with me. Reach out to me and let me know. I hope you all have a nice day.